Have you ever stopped to wonder why music hits us so hard? Why can a few simple notes completely change your mood? Well, today, we're going to pull back the curtain and look at the hidden physics behind it all. How simple vibrations become these incredible, soul-stirring symphonies.
Yeah, I know. It totally sounds like the setup for a bad science joke, right? But the answer is actually pretty profound. It connects these huge, epic symphonies with the tiniest little jitters of an atom. So, what's the connection? What do they have in common?
It's the fundamental laws of the universe. Seriously. The very same physics that governs how planets move and particles behave, that's the blueprint for music. It's kind of mind-blowing when you think about it, right? So let's dive in and see how this all actually works.
All right, Section 1, Music's secret ingredient, vibrations, the source of all sound. Okay, so to really get this, we've got to go back to basics, like square one. Where does any sound, and therefore all music, even come from?
Everything, and I mean everything, starts with a vibration. You pluck a guitar string, you hit a drum, you hum a tune with your vocal cords. All of those things are creating these little ripples in the air. We call them sound waves. So when you boil it all down, music is really just the art of organizing those vibrations in a cool way.
Okay, Section 2, the anatomy of a note. Let's look at the ingredients of a single sound. So we've got these vibrations, but how do we get from just a simple wobble to something we actually hear as a musical note? Let's break it down.
Well, the first key ingredient here is something called frequency. And it's pretty simple, really. It's just how fast that vibration is moving back and forth. You can think of it like a hummingbird's wings, right? The speed of that vibration is a physical thing, but our brains hear it as a musical thing, pitch. And what's so cool is that the relationship is super straightforward. A high frequency, that's a lot of vibrations per second, gives us a high pitch. Think of a piccolo. A low frequency, way fewer vibrations, gives us a low pitch, like a big tuba. It's this perfect one-to-one link between raw physics and what we actually hear as music.
Okay, but hold on. This brings up a really good question. If pitch is just frequency, why does the same exact note sound so different on a piano versus a guitar? A middle C is always the same frequency, right? It's about 261.6 vibrations a second, so the pitch is identical, but the sound itself, the character of it, is totally different. What's up with that?
So the secret ingredient here is something called harmonics. You might also hear them called overtones. See, when a guitar string vibrates, it isn't just moving up and down as one big piece. It's also vibrating in smaller sections at the same time, in halves, and thirds, and quarters. It's wild. And each of those little vibrations creates its own quieter, higher-pitched sound that stacks on top of the main note. That unique recipe of harmonics is what gives an instrument its personality, its timbre.
Just stop and think about that for a second. It means every single note you've ever heard isn't just one sound. It's actually a rich, complex chord of hidden frequencies all playing at once. It's the physics that lets us see this incredible depth and beauty that's hiding right there in plain sound.
All right, Section 3, how instruments make sound, the physics of musical machines. So, if music is all about wrangling vibrations and their harmonics, what does that make a musical instrument? Well, if you ask a physicist, they'd tell you it's a machine, a beautifully designed one, but a machine nonetheless.
Yep, every instrument you can think of, from a tiny flute to a massive grand piano, has the exact same job at its core, to give the musician total control over vibrations. They're just these really elegantly engineered tools for bending the laws of physics to make something beautiful.
Let's take a string instrument, like a guitar. The physics here is just so elegant. You want a higher pitch? Okay, you can make the string tighter, increase the tension. Or you can make it shorter by pressing your finger on a fret. You want a lower pitch? Simple. Use a thicker, heavier string. And that's literally it. Those three things, tension, length, and thickness, are all you need to get the entire musical range of a violin or a guitar. It's amazing. And this same basic idea applies across the board. For wind instruments, you're not vibrating a string, you're vibrating a column of air. A piano, it's this incredible machine with hammers and strings and this huge wooden soundboard that makes everything loud and rich. Even the classic curved body of a violin, that's not just for looks. It's a piece of acoustic engineering designed to resonate and totally transform the sound of the strings.
Okay, Section 4, the physics of the room, how space shapes sound. Now, creating the sound is really only half the story, because that sound then has to travel through a room to actually get to your ears. And it turns out the room isn't just a passive container, it's an active player in the music. And this is where we get into the field of acoustics. You've probably heard that word. It's basically the science of how sound behaves in a space. You know how sound waves bounce off hard walls, get soaked up by soft carpets, and even bend around corners. It's all about controlling how sound lives and breathes in any given environment.
You should really think of a great concert hall as a giant instrument that you, the audience, are sitting inside of. Every single curved panel, every material they chose for the seats, even the shape of the ceiling, none of it is an accident. It's all meticulously designed to control the physics of sound on this huge scale, all to make the music feel perfectly clear, rich, and just alive. Okay, Section 5. Why music makes us feel. The physics of emotion. So we've gone from a single tiny vibration to an instrument to an entire concert hall. But that brings us to the biggest, most important question of all, doesn't it? How does all this cold, hard physics create something so deeply human as emotion? Why does one chord sound happy and another one sound so sad?
Well, it all comes down to how different sound waves play with each other. When the frequencies of two notes have a really simple, clean mathematical ratio, their sound waves line up almost perfectly. Our brains love that orderliness. We hear it as something stable and pleasant. That's called consonance. But when the math is messy and complex, the waves clash and fight each other. We hear that as dissonance, and it creates this feeling of tension, of unresolvedness.
And the most perfect example of this is the octave. The higher note vibrates at exactly twice the frequency of the lower one, a perfect 2-to-1 ratio. The physics is so clean, so simple, that our brains basically hear them as the same note, just higher. This beautiful, simple math is the physical backbone of all musical harmony.
So when you think about it, a song is really just a story told in the language of physics. A composer is a master at taking us on an emotional journey. They guide us through these moments of physical tension, that dissonance, and then give us that satisfying feeling of release by resolving it into stability, the consonance. The whole emotional ride of a song is literally built on these controlled patterns of clashing and resolving sound waves.
And that kind of leaves us with one last big question to think about. If all the beauty and all the emotion in music can be traced back to the simple math of physics, does that make it less magical? Or does understanding the incredible, elegant science behind it all actually make the magic even more real, even more profound? Something to think about. Thanks for joining me.